Hey guys, it's Mr. Lineski with Chapter 22. We are looking at comparing two proportion z-tests. Sometimes we call it a two-prop z-test. The good news is that you basically know about 90% of this chapter already. So most of it's going to seem very familiar. We're just going to kind of spice in some added stuff. So we're still doing the four-box method of hypothesis, conditions, mechanics, conclusion. So we're going to kind of just talk about what's new. So what's new in this chapter is that instead of just sort of doing one trial and saying, oh, you know, the globe and comparing it to Earth, we're sort of now comparing two groups of things. So essentially that means we're going to have two of everything. We're going to use the subscripts to sort of differentiate between the different populations. So typically at some point in the HOHA, box number 1, you're going to have to specify that P sub 1 is equal to the proportion of whatever, and then P sub 2 is equal to the proportion of, and then whatever the other group is. So I just used men and women as an example. The idea behind the two-prop z-test is that we're always testing, is there a significant difference between the two groups? And that's sort of what our hypothesis is stating. So your null hypothesis is always going to be that P sub 1 minus P sub 2 is equal to 0. The reason for that is that we're saying there's not a significant difference between the two of them. In other words, they're roughly the same. The independence condition is going to change slightly, nothing crazy, and then instead of using a one-prop z-test, we're going to use a two-prop z-test. We're also going to look today at confidence intervals and how they are related to two different groups. So we'll kind of take a peek at some of that stuff in the video here. We're doing comparisons between two percentages, and this is typically much more common in the real world, and it's obviously a little bit more interesting too. We often want to know how two groups are differing from each other. We typically want to know if something like if a treatment is better than a placebo, or whether this year's results were better than last year's. So the idea here is that standard deviations don't add, but the variances do. So we looked at standard error formula for a one-prop z-test. So that equation is actually going to change a little bit when we're now looking at the differences between two proportions. So the equation that we're actually going to use there, typically we denote it as standard error of P1 minus P2, and that's going to equal the square root of P1 Q1 divided by N1, and then plus P2 times Q2 divided by N2. So just as a reminder, we sort of have these two different groups now. P1, so that means there's a Q1, and then if there's a P2, there has to be a Q2. The sample sizes can be the same sometimes, but sometimes they are different. In fact, most times they're actually different. So that's actually the formula you're going to use now to find standard error. So when you're checking your conditions, you want to make sure that you're checking them for both populations. Something you might want to say is that the two groups that you're comparing have to be independent of each other. Before we would just say that the people in the samples were independent. Now we actually have to say that, you know, proportion 1 is independent of proportion 2. With NP-NQ condition, that means you're going to have to check that twice now as well. And so basically when you're checking conditions, it's just going to get a little bit more wordy now because there's two groups of things happening. I wanted to show you an example of, well, what would it look like if two groups weren't independent? And so here's an example of where it wouldn't be independent, and that might be something to raise suspicion on, you know, if a condition's not met. So if one of our groups was the proportion of people who own an SUV versus the proportion of people who think that a tax on gas should increase. And so hopefully it's a kind of known fact that SUVs tend to use more gasoline than most other vehicles. And so those kind of groups would not necessarily be independent of each other. So again, assuming that all the conditions are met, we can still use a normal model. So now the normal model is going to look a little bit different now that we're doing two proportions. And as I want to remind you that the null is driving the normal model. And so the null again is that P1 minus P2 equals 0. So what exactly does that mean about the center of our graph? The center of the graph is actually going to be at 0. So whenever we look at that normal model now, the center is going to be at 0. So that means that we're going to have some positive values and we're going to have some negative values. Keep in mind we're still talking about proportions, and so some of you at one point were getting negative proportions, and this is actually now an example where we're allowed to have negative proportions. As I mentioned before, the standard error or standard deviation, that's just going to be our formula that I mentioned earlier of P1 minus P2, and that's going to be P1 Q1 divided by N1 plus P2 Q2 divided by N2. This is a formula that you will get on the formula sheet, I believe, for the AP test. Oops, sorry, I forgot the hats. These should have little hats on them as well. Okay. Is that on here? Yeah. So now how does a confidence interval change? So I've mentioned that we're going to look at confidence intervals for these two groups. The confidence interval, our formula for that used to be p hat plus or minus z crit times standard error. It still looks like that, but now our p hat essentially is going to be p hat 1 minus p hat 2, and then plus or minus the z critical value, so that kind of stays the same, and then it's going to be times our standard error. Again, standard error is this here. So the formula is going to look a little bit different because, again, we're doing two groups. The good news is that you will never have to do that by hand because our calculator does it. It is when you go to stat, you go to calculate, and it is called 2-prop z interval. And basically you just type in the information that you have, and it shoots out the interval for you. So we're going to talk a little bit about what some of those intervals might look like. Let me get this thing out of the way. Nope, that's not going anywhere. Okay. So I just wanted to give you a couple examples on how to interpret these confidence intervals because it is a little bit weird sounding. So it says for this sample, let's assume that P sub 1 represents a women's ability to complete a task, or the proportion of women who are able to complete a task. And then P sub 2 will be a proportion of men's ability to complete a task. So if we were testing the null, P2 minus P1 equals 0, and the alternate of P2 minus P1 is greater than 0, and we're going to use a 95% confidence level. So what I want to point out again here that P2 is men's ability. So if I'm taking the men's ability minus the women's ability and it's coming out as a number greater than 0, meaning it's a positive number, that is essentially in terms of what we're trying to test. We're trying to test is the proportion of men's ability to complete the task higher than the proportion of women. So here's just kind of a quick example. So here's an example of what the confidence interval might look like. So notice we have a negative number and we have a positive number. If I had to interpret that, we would say we're 95% confident the proportion of men who completed this task is between 11.2% less and 8.3% more than the proportion of women who completed the task. So notice that I talked about the men first, because that's sort of the group that we're discussing first. I used the word less with the number that came out negative, and I used the word more with the number that came out positive. So here's another example that could potentially happen if I get two negative numbers. So notice I would convert these two percentages, and it would be 34% and about 2.1%. So if I had to interpret this, I would say we're 95% confident the proportion of men who completed this task is between 2.1% and 34% less than the proportion of women who completed the task. So if you notice here, both of these numbers were negative, so I just kind of used the word less after both of those numbers. So this was if we were thinking in terms of the men first, but realistically, there's no rule that says, oh, the women had to be P1 and the men had to be P2. And so anytime we look at a confidence interval in this chapter, your answer might be kind of the opposite of mine, depending on if our groups are flipped. So let's say that we actually flipped the groups and we were talking about the women first. For this particular interval, if we were talking about the women first, we would say we're 95% confident the proportion of women who completed the task is between 2.1% and 34% more than the men who completed the task. So for confidence intervals, when we're comparing these two groups, if 0 is in the confidence interval, that means we're likely going to be failing to reject the null, whereas if 0 is not in the confidence interval, that means we're going to reject our null. So like if you go back and take a look at these, this one contained 0 or 0%, so I would have failed to reject the null here, whereas this is saying that, oh, it was both less than the proportion of women, and so we would reject the null there. So that's a little bit about confidence intervals. So remember, they didn't go away. They're coming back. Okay, so now let's take a look at our 4-box problem. We'll kind of go through 2 of these together. I want to show you sort of a long way and then an abbreviated way on how we can handle now that we have 2 groups. So this first problem says a group of students who had never smoked were questioned about their parents' attitudes toward smoking. These students were questioned again 2 years later to see if they had started smoking. The researchers found that among the 284 students who indicated that their parents disapproved of kids smoking, 54 had become established smokers. Among 41 students who initially said their parents were lenient about smoking, 11 became smokers. Do these data provide strong evidence that parental attitude influences teenagers' decisions about smoking? So, the only thing I'm going to kind of, as we go through the boxes here, talk about what is being added, what's changing. So notice in the HOHA, it's not just the HOHA and me explaining the null now. I also have to define what P1 and P2 are. So P1 would represent the proportion of kids who smoke whose parents disapproved of smoking. P2 would represent proportion of kids who smoke whose parents were lenient on smoking. Now again, is there a rule that says, oh, disapprove has to be first and then lenient has to be second? No. For this one, we are just testing, is there a difference? So that would be does not equal to. Forgot to put the slashes in there. I'm going to recommend that you write the HOHA like this, but occasionally you may see it written this way. Because again, if you think algebraically, I can add P2 to both sides, and that would just say P1 equals P2. So if you want to write them this way, that's fine. The reason that I like writing it this way is that the 0 is kind of a reminder of how is the graph centered. The model. The model, again, is always centered at 0. So I think this is kind of a better one to remind you of that. So the null claims that there is no difference in the proportion of teens who smoke based on parental attitudes. The alternate says that there is a difference. So remember, you don't really need to put a ton of context in that second sentence. It can just be very brief and to the point. So again, what was new in box number 1? We kind of had to add this stuff here. That was something new. So now our conditions. If we look at the conditions, it says teens from each group are assumed to be randomly selected. The parents who disapprove of smoking are independent of the parents who are lenient on the matter. So notice that was sort of our independence. We're not saying that the parents who were selected were independent. It was parents from group 1 are independent of parents from group 2. You can refer to things now as group 1 and group 2 as long as you sort of establish P1 and P2. It's sort of understood what you're referring to. Group 1 had 54 smokers and 230 non-smokers. Group 2 had 11 smokers and 30 non-smokers. So this is me checking NP, NQ. A lot of you are just writing NP equals 54, and you're not really explaining in context what that actually is. And that's not really a great thing. You should kind of explain in context what that's referring to. Get rid of that. So all of those are greater than 10, and then we can assume that the teens surveyed are less than 10% of the population of teenagers that exist. So all of our conditions are met, therefore we'll use a normal model and we'll conduct a 2-prop z-test. So what does that look like now? So I'm going to pull up the calculator here to show you all what the 2-prop z-test looks like. So if you go on your calculator to stat, and then you go to tests, and it is number 6. So this is kind of what it looks like. This is what we're going to be asking for, x1, n1, x2, n2. And then notice we're kind of assessing our not equal to, less than, greater than situation. So what do you need to write down? Basically what you're typing in, x1, n1, x2, n2. So for this one, let me look at my paper here, we would say that x1 is 54, n1 is going to be 284, x2 is 11, and then n2 is 41. For this particular test, we were checking, is there a significant difference? So it's not saying increasing or decreasing. So that's a two-tailed test. And then we'll go down and we'll just hit calculate. But same thing, you can always draw the model and it shows you what that looks like. Hey, a domain error. What happened? Let's check. Probably typed something in wrong. 2-prop z-test. Oh, what happened here? Sorry, 284. I'm not sure what happened with that. This should be 11, and that should be 41. Sorry about that. And just hit calculate. There we go. So just like we always kind of do, we should mention what the z-score is, so negative 1.17 roughly. This still represents our p-value, which again is the probability that that particular sample occurs. You should also then state what p-hat1 is and p-hat2 is, because keep in mind you do have to calculate that standard error, which is what I do down here. So again, that's just using the p-hats, the q-hats, the n1, and the n2. Okay, so let's take a look at that p-value. Keep in mind that's what we really want to kind of focus our attention on. So that p-value is about 24%. Notice the problem didn't really specify which significance level to use, so we'll use 5%. And so our conclusions basically stay the same. So since that value is greater than 5%, we fail to reject the null. There's not enough evidence to support that there is no difference in the proportion of smokers based on parents' attitudes. So this little section right here, I wanted to show you this. So it says there's a 24% chance of seeing the observed difference by natural variation. This little sentence right here is the explanation of the p-value. So you may see some multiple choice questions that ask you to interpret the p-value. That's kind of what you would say if you were interpreting a p-value. Okay, so I'm not going to go through the entire next problem with you, but I do just want to show you how you can shorten some stuff up a bit. And basically it's in box 1, because box 1 was a bit wordy. So instead of separately defining P1 and P2, I want to show you the next problem. So I'll read the problem and then we'll kind of talk about how you can shorten it up a bit. So it says in a random sample of 500 people aged 20 to 24, 22 were smokers. In a random sample of 450 people aged 25 to 29, 14% were smokers. So then they want to know, do the data provide sufficient evidence to conclude that the proportion of smokers in the group 20 to 24 is higher than the proportion of smokers 25 to 29, and then use the significance level. So if they're saying that this number is higher, when I subtract the two groups, this minus this should result in a positive number. Therefore, we're saying it's greater than 0. So notice what I kind of snuck in here. I didn't take time to separately define what P1 and P2 were, but when I was describing my HOHA, once I established what group 1 was, the proportion of smokers aged 20 to 24, you just sneak in a little P1 there and kind of say, hey, this is what I'm calling P1. The smokers aged 25 to 29, sneak in a little P2 there. And then again, just kind of state your alternate. So now once you establish that, you can kind of refer to these groups as group 1, group 2. So like I said, I'm not really going to go through the whole shebang with you here, but I'll just kind of show you everything that's on this. So all of our conditions are met. There's nothing really crazy there. We run our test. We get a p-value here of 0.0007, which is really small. So since that's a small level, I believe in this problem, it did say use a significance level of 0.01. So that is our alpha level. So sometimes in box 3, you may want to define what alpha is. If you don't do it in box 3, at least do it in box 4. Say, we're using 1%, 5%. So this problem specified which alpha level to use. So since it is less than 1%, we do reject the null. There's enough evidence to support the claim that the proportion of smokers aged 20 to 24 is higher than smokers aged 25 to 29. All right, so that is it for Chapter 22. Thank you for watching. I hope it helped. Have a good one.